Okay, let's get started. First of all, any questions, comments? Yeah.
When do you expect lecture 7 to be posted? The last lecture, when do you expect it to be posted on YouTube?
Yeah, I will. Yeah, I think I posted until lecture 6 now.
Okay.
Yeah, so yeah, just take some time to process it. Yeah, so I should be able to, I think, upload the lecture 7 by the end of today or tomorrow morning. So that's my plan. Yeah, there's something happened in the lecture 7. Yeah, I forgot to record it in the first place, and we missed like 20 minutes. But I have the sound. So yeah, basically that part is a review of the previous lecture. And yeah, I will synchronize that with the slides. So that needs a bit more processing. So it takes a bit more time. Yeah, okay, very good. Yeah, so any other questions, comments? Oh, by the way, I posted the material of lecture 7, 8 already, so you can take a look at that if you want. Okay, so let's do a brief review of the previous lecture. So in the last lecture, we start by talking about the Fourier transform of a periodic signal, right? So basically, so from now on, so we're now going to do match Fourier series analysis. All we do is Fourier transform, okay? The reason that we can do it is that we can do the Fourier transform for the periodic signal that we care about, okay? And here's how we do that. So first of all, we know this Fourier transform pairs, right? So that's very important. So if we do a phase shift in the time domain, then that will result in a frequency shift in the frequency domain, right? So in this particular case, so for a complex exponential in the time domain, then it will be a shifted delta signal in the frequency domain, right? So that's very important, and that's basically why we can do the Fourier transform of a periodic signal, right? You can see that. So this guy is nothing but a periodic signal, right? The cosine plus j times sine. Okay, and here's how we do that. So this is a signal in the time domain, right? If it's a periodic signal, so let's say, you know, in the ideal case, so it can be written as Fourier series, right? And then, so by using the linearity property of the Fourier transform operator, so we can get this, right? The Fourier transform of this guy is nothing but the Fourier coefficient, summation of the Fourier coefficients multiply this guy, right? So that's the Fourier transform of the complex exponential, right? And we know its Fourier transform is a delta signal. Then, oh, I missed the summation here. So basically, then the Fourier transform of this guy is a summation over n of this guy, right? So I missed the summation here, right? So here should be a summation over n of this guy, right? Because, you know, this guy, we get this from here, right? So yeah, I'll fix it offline. Okay, and by using this, so we can get a very nice kind of Fourier transform pair for a summation of a delta signal. Okay, so if I have a summation of a bunch of delta signal, right, it's like infinite number of delta signal, right, and this Fourier transform is another summation of delta signal. Okay, so they are very symmetric, right? You can see that here the fundamental period is T naught, and here for this signal the fundamental period is F naught. Okay, and the only difference here is that we have a scaling here, right? It's 1 over T naught, where T naught is the fundamental period, right? The reason we have this T naught is nothing but its Fourier series coefficients is 1 over T naught. Okay, if you compute the Fourier coefficient of this guy, you can get 1 over T naught for all n's, right? So in this case, the Fourier coefficients is not a function of n. Okay, that's why we have this 1 over T naught. Okay, and another interesting thing here is that we can represent a summation of a bunch of direct delta signal by a summation of a bunch of complex exponential. Okay, so this also explains the relationship between these two signals. Okay, which is kind of weird, right? But you know, in practice, you know, we in many cases we have this kind of scenario all the time, and when we see that, we know, okay, so if we have this summation, then we can write that as this. Okay. So which is pretty nice. All right, and then we talk about another two topics. So one topic is that it's about bandwidth. So we see a bandwidth example, and then we see more properties of the Fourier transform. In particular, we see the time scaling property, okay? So in this case, basically, we consider if a signal in the time domain is a square waveform, okay, just square waveform, right? It's not periodic or anything like that, right? And in the frequency domain, so we compute that, so that is nothing but a sync signal, right? So you can see the lecture notes about that, and we define the first, the point of the first zero crossing point, so that would be our bandwidth, right, in this case. So that'll be like 1 over tau in this case, and then we see another example of modulated square pulse. Basically, we use GT multiply cosine, right? Then we shift that to the left and to the right, and then reduce the magnitude by amount of 2, right? And in that case, we can see that the bandwidth doubled, right? Because here the bandwidth is defined by the positive part of the frequency, right? We ignore the negative frequency, okay? And that's an example to compute the bandwidth. And then we talk about the time scaling property of the Fourier transform. So basically, if we have a time scaling here in front of t, right, in this case, so imagine that if a is bigger than 1, right, in this case, it's like we widen the signal or we narrow the signal if a is bigger than 1. Right, we widen it or we make it narrower. If a, I say if a is 2.
If it's bigger than 1, you'll make it wider. If it's smaller than 1, you'll narrow it, right?
Is that right? Any different opinions? Yeah, maybe let's make it clear, right? It's very important. So let's consider square waveform like this, GT, just like this, right? Let's say here's -half, here's half, and here's 1, here's t. Okay, so that's our square waveform. So now let's draw the picture of tau 2t. Okay, what does that look like, right? How to solve this problem? Right, so normally, when we have this very nice shape, so we just look at the corner point here, right? How about we look at this point? Okay, so here when t equals to half, it'll be like this point, right? And in this case, so basically it means that 2t equals to half, it'll be this point, right? If 2t equals to half, then t equals to fourth, right? Okay, then it means that so this point is 1 over 4. Similarly, so negative part is also 1 over 4. Then we have this square waveform. Okay, so there's still 1. So this is 1 over 4. Here is 1/2. Then if we do a 2 here, so make it wider or narrower? Narrower, right? So it's the opposite, right? So if a is bigger than 2, we make the signal narrower. That makes sense? Okay, great. Yeah, and if we do that, and then we compute the Fourier transform of it, so by doing some algebra, so this is what we can get. Okay, so for the Fourier transform, and we need a scaling of 1 over a here, and then we have f here, then here is f over a, right? Again, let me ask you a question. So if a is 2, right, in the time domain, it is narrower. So in the frequency domain, what happened? It's wider or narrower? Wider, right? It's the opposite, right? Here we times a, here we divide by a, right? Yeah, example, we didn't see the example, right, in the last lecture. So we finished here, right? Yeah, this is what I remember. Yeah, let's see example. Basically, the example we're gonna see is like exactly like this example, okay? Okay, good. Yeah, let's finish the example first. So this is our example. So let's say this is our signal. This is in the time domain, right? In the frequency domain, it will be like what? Sync signal, right? So hopefully, yeah, let's get very fluent with this Fourier transform pair, right? Because we're gonna use it so many times in our lab. I think including lab 2. So we're gonna still focusing on that because that is so important in wireless communication. And remember that, so here in this case, so that is like 1 over tau. In this case, it's 1 over tau, right? And if we draw in this way, so what is tau? Yeah, what is tau in this case? So in this case, tau is just 1, right? Because this is standard, right? So so normally we write that as t over tau. Okay, so that's the more general version of it. So if we write just t here, so it's a standard square wave, tau is 1. Right? If tau is 1, so we have this guy equals to 1, and this guy equals to 1, right? And we call this, so this distance is basically our bandwidth, in this case, equals to 1. Okay, and here's 1, so let's write this is GF. Okay, so now let's see what happened if we make it narrower, right? If we make it narrower, then in the frequency domain, yeah, let's denote that. So if I have a 2t here, that will be GF over 2, right? Then we're going to make it wider, right? So basically, that'll become like this, right? 0, and oh, there's like 1 over 2 here, right? So that's 1 over 2, and this guy becomes 2, and this guy becomes minus 2, right? So in the frequency domain, we make it wider. Okay, then the bandwidth now becomes wider, becomes b equals to 2 now instead of 1. Okay, so now let's think about it. Does that make sense? Right? Why that makes sense? Mathematically makes sense, right? But physically, does it make sense? Meaning that, so now let's say if we transmit a bunch of square waveform, right? Let's say if we transmit that, it means 1. If we transmit like this, it means minus 1, for example. Okay, or 0, right? Okay, and then we send a bunch of square waveforms. If we narrow it, what does it mean? That means that in a fixed time, we can transmit more information, more square waveform, because it's narrower, right? So in a fixed time, if we can transmit more square waveform, it means that it changed faster, or twice as fast as this one. Okay, if it changed twice as fast, then we need a more frequency component, right? Then the frequency actually, we need like twice of the frequency, right? Sort of makes sense, right? It's not accurate, it's intuition, right? But that's basically the idea of it, right? So basically, there's no free lunch, right? So if in the time domain you make it narrower, right, like by a factor of 10, and then in the frequency domain you need wider, you need by a factor of 10 more frequency component. Okay, right? So this is like this relationship, right? You cannot make a signal both in the time and frequency efficient, right? There's no such a thing that in the time domain you can transmit more, and in the frequency domain you can use lesser frequency, right? There's a trade-off there. Okay. Okay, great. That's the example we need to talk about, and then, yeah, let's talk about something else. Yeah, basically, these are the 3 topics in today's class. Let's see how far we can go. And the first topic is we'll continue talking about Fourier transform properties. So here we talk about time scaling property, and then we're going to talk about next one is the time shifting property. Okay, and then we'll talk about so is that possible to compute energy and power in the frequency domain instead of in the time domain? Right? We know how to compute the power and the frequency in the time domain. Right? We know if we do an integral of the signal square, then we get the energy. Right? And if we, for the power, let's say for a periodic signal, if we do compute the energy in one fundamental period and then normalize it by the length of the period, we'll get the power. Right? We know how to compute in the time domain. Right? Today we're going to see how we can compute that in the frequency domain. Okay? Would that be easier or harder? Yeah, and then so we're going to talk about energy spectrum density. So those are extremely important concepts. So you're going to have something like that in your homework. Yeah, the reason we want to talk about all this concept is that those are just simpler metric to measure the property of signal or system. Okay, that's why we need all of those metrics. Okay, and so now let's see the first one. So next we're gonna see the time shifting property. Property. Okay. Yeah, for the time shifting property, it is basically like if we shift the signal in the time domain, then we want to know what will happen in the frequency domain, right? So yeah, we should have seen this kind of thing many times, right? So let's see whether you can tell me directly. Let's say if we have a signal GT, and we shift the signal. Yeah, let's assume that it's not periodic, right? So if we shift the signal in the time domain by T0, and then we do a Fourier transform, so what is going to happen in the frequency domain? Yeah, you don't need to tell me exactly the formula, but intuitively, what will happen? So we have seen that if the signal shift in the frequency domain, then in time, we have a phase shift, right? And since the forward and the inverse Fourier transform look so similar, it means that if we have a shift in the time domain, then in the frequency we should have a phase shift, right? The sign will be different, right? But it will be roughly a phase shift. Okay, so that's basically the idea. Now let's compute it. So the computation is nothing but using the definition, right? We just have this e minus j 2 pi ft dt. Okay, remember, so now it's a forward Fourier transform, so now we have a minus sign here. Okay, if it's inverse Fourier transform, we don't have this minus sign, we have a positive sign. Okay, and next, yeah, again, because we need to cook up gt, right? Because we want to use g of f to represent this guy, right? So we need some gt. So basically, now we have a t minus t now, so that's not what we want, right? We just use substitution. So we let, for example, u equals to t minus t naught. Okay, and then we have g of u here. Okay, if we do that, then we can see that t equals to u plus t naught. Okay, and dt, dt just equals to du, right? So they're not changing. Okay, and if we do that, and the integral limit here will not be changed, right? Because we just shift by a fixed amount, right? By a fixed amount. So then what will change is here, right? So minus j 2 pi f. So t equals to u plus t naught, okay, dt, right? And now we can move, this t naught out of the integral because that's not a function of u, right? We just move this t naught out of the integral, though. So we have e minus j 2 pi f u as t naught. Okay, and then we have the integral gu e minus j 2 pi ft dt. U. I always mess that up. U du. Okay, yeah, this is t naught. It looks like f naught, t naught. Okay, and clearly, so this part is the definition of GF, right? So that's our GF. Okay, then we know this guy eventually equals to this phase shift. GF. Okay, so we just have this phase shift. And the amount of shift is a negative sign. We have negative sign there. Just be careful on that. Okay, and yeah, since the phase shift is a linear function of this t naught, we call that a linear phase shift, right? Because it's some constant multiply t naught, or something multiply. Oh, sorry, something multiply f naught, not t naught, right? So yeah, f is a variable here. Yeah, f is a variable here, so it's some constant multiply f. Okay, that's why it's called linear phase shift. Right. Any question? Okay. Yeah, if no, let's continue. So now we're going to see two examples. So one example is it's called distortionless transmission, and the other example is transmission with distortion. Okay. Yeah, that clear? Okay, so first let's see what is a distortionless transmission. Okay, so Yeah, we're going to define what is this distortionless transmission later. So basically, distortionless basically means that, okay, after the transmission, so we can recover the signal exactly without any distortion, okay? In other words, yeah, we're going to see the definition. So before that, we need to introduce some notation here. So let's assume that our signal, we have an energy signal, x of t. So this signal is what we want to transmit it, and its Fourier transform is x of f, right? And then we have a linear system or a LTI system, right? In wireless, so this is our channel, right? So we're, system basically means channel. You can imagine that as our channel. Okay, and the channel unit impulse response is denoted by h of t, and then its Fourier transform is h of f, right? And then, so what do we, and therefore, the output is nothing but in the frequency domain. So we compute that in the frequency because that is easier, right? Y of f, so that's our output signal. So that equals to what? Can you tell me in terms of h and x?
The products.
Very good. The product, right? Because of the property of the convolution. Yeah. Any question on this? Does that make sense to everyone? Very important, right? So this is a very basic concept, right? So we need to know that. Yeah, most of the analysis in our class is in the frequency domain, right? Because that is more intuitive and it's easier to analyze. Okay, so yeah, now let's take a deeper look on that. So basically, this is our output signal, right? So our output signal, we can rewrite it as what? So this signal is normally a complex signal, okay? So imagine that even, in the time domain is real, then in the frequency domain, it could still be complex, right? There's some symmetric property, but still complex. So we have another way to represent our complex signal, which is using the magnitude, which is the absolute value of y of f, and then multiply the phase. So phase is also a function of f, right? So this is another polar representation of the complex number. So here, everything is a function of f. Okay, and then we plug this in here. So basically, that equals to, we have a h of f multiply x of f, right? And then, so for each of this signal, so we can represent that as h of f, and then times ej theta hf, right? And for x, we can write that as x of f ej theta xf, right? Then, so now we take this magnitude in front of it, and then for the phase, so we have this and that left, right? So that's basically j theta h of f e j theta c x of f, right? So now it's a magnitude and multiply, the phase term, right? So we can combine this. Okay, so yeah, let's combine this here, make it easier. So basically, j theta h plus theta x of f, right? And now we represent our output signal as the magnitude multiply the phase part, or the angle part. Okay, and by comparing these two, yeah, we can easily see that our magnitude equals to basically this part, which is easy to compute, right? HF, XF. Okay, and our phase part, YF, equals to this guy, right? Theta HF plus theta XF, right? Is that correct? Any question? Doubt? All right? Everybody agrees? Really? Not quite, right? So yeah, I mean, this part, there's no any problem, right? But for this one, we just write like that. But we need to, plus minus k times pi normally in practice to make sure this guy is fell in between minus pi to pi, right? Because the angle part is always tricky, so there's a range on that, right? There's no like 3 pi, right? You have to make it minus pi to pi, then, if we get out of the range, we need to add some pi's or minus some pi's to make it, right? But yeah, that's just minor thing. Yeah, roughly speaking, we can still write that, but just to make sure that it is that, but we need to make sure this guy is in the range of minus pi to pi, okay? In the range of minus pi to pi, right? We need to guarantee that, okay? Yeah, good. Okay, yeah, this is some basics, right? Okay, so after this, yeah, let's write it there. All right, so now let's define, so what is distortionless transmission? Okay, so distortionless transmission is nothing but y of t just equals to some constant k multiply x t minus t naught. Okay, that's it, right? We can manipulate the magnitude by a constant, and then we can shift the signal, right? So that's distortionless communication or transmission. Okay, so our goal is that, okay, let's analyze what is the system look like, right? Or what is the channel look like, right? If y equals to k times x t minus t naught, and then what is h look like, right? Or in other words, what is the magnitude of h? What is the phase of h? Okay, both of them are important. Okay, let's see whether we can do that or not. Yeah, let's assume for simplicity, right? Let's assume that, I use TD here, right? Means delay. So let's say this is a real signal, okay, for simplicity. Okay, yeah, and now let's see in the frequency domain, YF in this case, let's see what that equals to, right? Because of this simple format, we can write down that directly, right? So the k will now change, right, because of linearity property of the Fourier transform, okay? And for xt minus td, what would be that in terms of xf, right? We just learned that, right? So in the time domain, we do a shift. Then in the frequency, it will be a phase shift, right? In this case, right, it'll be like minus j 2 pi f td, right? So that's basically it. All right, okay, and yeah, from this formula, we can see that h is nothing but y over x, right? So we can compute h in this case, right? So h of f is nothing but yf over xf, right? We divided xf on the other side, and then we have k e minus j 2 pi f td. Okay? Yeah, for simplicity, let's assume k is real and bigger than 0, right, to not have any trouble, right? So that's our h. Okay, so in this case, can we compute what is hf, the magnitude? So that is, right, this part, right? Okay, and then what is the phase of h? What is phase of h? So that's nothing but this part, right? So that's minus, yeah, I didn't write anything stupid. Okay, minus 2 pi f td. And also we need to kind of be careful here. So we need to plus minus k pi here, right? To make it within the range of minus pi to pi, right? This is tedious, but be careful on that. Okay, that's basically how we compute the magnitude and the phase for distortionless transmission. Okay, it's pretty simple, right? But the idea is from here, right? So we're gonna compute a lot of this and that, right? So in practice, both of them are important, right? So when because h of f is a complex signal, right? You cannot draw it normally. And normally we don't draw the real and the complex part because we can see nothing from there, right? So what we usually do in practice is to draw the magnitude and the phase. Okay, both of them are important. For different application, it is possible that one might be more important than the other, right? But normally both of them are pretty important. And so what I wrote here is that the human ear is less sensitive to the phase distortion. Okay, so ear is less sensitive to the phase distortion. It's more sensitive to the magnitude. Okay, on the other hand, our eyes is more sensitive to the phase distortion. Okay, compared to the magnitude, right? So yeah, I think I have no idea that's why, but probably that's physics. Okay, but the point is that either both of them can be important, right? So we don't want to just care about one of them. Okay, all right. So this is distortionless transmission. So now let's see what is nonlinear distortion. So in this case, basically, we can pretty much recover the signal very easily, right? So we just times a constant and then shift that a little bit, right? But in some cases, right, if the system is not LTI, it's nonlinear, then it may be harder to recover the original signal, and the distortion may be more troublesome. Okay, so basically, this is one kind of system that we want to consider. So let's say, let's consider an operator. So that's our system, right? We didn't write that as an H, right? Because normally H means LTI system, right? It's the F of something, right? So here is our input G of t, right? So this is our system function, okay? So specifically, let's consider when F of, when F is basically Ft equals to xt, gt to the power of k, right? That's what happened in the system, right? We just raise g of t by power k. Yeah, let's see what will happen for that, right? So this is nonlinear distortion. Yeah, we need to write it. So that is nonlinear distortion. Okay, yeah, for a nonlinear distortion, again, so let's say after the system, so this will be our output, right? So that equals to y of t, okay? And now let's see, okay, in the time domain, so basically it's very hard to see what is really happening, right? We just raise this by power of t, but let's see whether we can see anything from the frequency domain, okay? So basically what we do is nothing but we compute y of f, right? So y of f is nothing but the Fourier transform of gt, okay? Okay, again, our idea is to represent this guy using GF, right? So how can we do that? Any ideas? Right, let's see what that equals to, right? So that equals to GT multiply GT again until K GTs, right? So this is a bunch of multiplication, right? So I want to compute the Fourier transform of a bunch of multiplication, right? In other words, if it's a multiplication in the time domain, what happened in the frequency domain? Convolution, right? So if we have two items here, then in the frequency, it will be GF convolutes GF, right? So now we have K terms here, right? We just write it convolutes itself K times, right? So I have K terms here, right? So in the time domain, it's multiplication. In the frequency, it's just convolution. Is that clear? Right? So now we want to see what will happen for the bandwidth, right? Let's see the bandwidth for GT. So its bandwidth equals to B, right? Then can you tell me what is bandwidth for this guy? right? Let's try to derive it, right? So normally when we think about this problem, we think we convolute two square waveform, right? Let's say we convolute two square waveform. Here's from 0 to A, and then another one like this from 0 to B. Okay, so if we convolute between these two guys, then what will happen? Right, we shift this guy and then move inside, right? So basically, what we're going to get is nothing but this shape, right? Right, so basically, can you tell me what is the value here? Let's say here 0. So what is the value here? Right, we flip this guy and then move it until somewhere here. So that will achieve this point, right? Therefore, this point would be B, right? And what is the value of this point? We move it until everything is out. Very good. B plus A, right? So it basically means that if we do a convolution between this and that, the width would be the summation of the width of these two guys. Does that make sense? So the convolution will make the width of the signal wider. Does that make sense? Okay, so now if A equals to B, it will be 2A or 2B, right? So now can you answer the question? Very good, right? If the bandwidth for a single one of them is B, then the bandwidth of this guy is K times B. So it got K times wider, right? Which is not good. Okay, so basically, this behavior, after some system, after some processing, so we have new frequency component. So this is called, we have special term for it. It's called spectral regrowth. Okay, we have the exact definition in my notes, but the meaning of it is nothing but this. It's called spectral regrowth, right? It means that it grows some new frequency component, so which is not desired. Okay, that's bad. So I want to get rid of those. Okay, right? So that's basically the idea. So any questions? Okay, if no question. Yeah, I think I'm going pretty fast, right? So if just, you need to work a little bit after class, right? We have so much content in this class, so can't go too slowly. All right. Okay, so let's continue. So now we're going to see how can we compute the power and energy in the frequency domain. Okay. So how we can compute power and energy in the frequency domain. Okay, so let's get started. So let's assume we have a periodic signal and denoted by S of t. So that is a periodic and with fundamental frequency of fundamental period of t naught. So now let's compute its power, right? Let's see the definition of it. So the power of this guy is nothing but, we need to compute the energy. So that is like this. We do the integral over one period. It doesn't matter which period, right? Just one fundamental period, right? We can put A as 0 here or as minus t naught over 2. It doesn't matter at all here, right? So this is the energy over one fundamental period, right? So for the power, is the energy of unit time. So we need to divide it by 1 over t naught. So that's the definition of power for a periodic signal, right? Still remember that? Good. Okay, so now let's manipulate. So our goal is to see whether we can compute this guy using its Fourier series, right, in the frequency domain, right? Let's see whether it's possible or not. Okay, so in order to do that, so basically, what we're going to do is that we're going to use the Fourier series to represent this guy, right? So basically, that's summation over n. And we have Sn e j 2 pi n f naught t square dt. Right, we just replace this guy by its Fourier series, right? And from now on, we're going to use a complex Fourier series, right? And now let's see what we're going to do next. So basically, next we're going to break this guy, right? So now, so we have like many terms here, multiply many terms conjugate, right? And then we definitely have many this kind of term, right? Sn, E, J, 2 pi, N, F naught T. So we have some this kind of term left, for sure, right? But how about the other terms, the cross term, like 1 and like S1 times S2 conjugate, this kind of cross term. So what happened to those kind of terms? Can you take a guess? Right, remember, so for this guy, for the complex exponential, so we call that frequency basis, right? So one important property of the frequency basis is that, so if we use 1, multiply another one that is different by this one, and do the integral over one period, that will give us 0. Okay, it means that all the other cross term will be 0, right? So if you don't believe me, just try it. I think you have seen some of those in your lab or in your homework. So basically, everything else is 0. This is what left. Okay, so basically, we can take this sum out, right? Everything else will be 0 because of the property of the frequency basis. All right, okay, and next. So we're going to break, because this is a complex number, we're going to break it into its magnitude, and then multiply the phase absolute value. So we have a square here, and dt. And then what is the value of this guy? 1, right? Very good. And then 1 over T naught. And yeah, we can take this summation out. Don't need that. Yeah, let's take summation out. 1 over T naught. Okay, so now it's pretty nice, right? So this is not a function of t. Okay, just constant. We'll just take that out, right? So that's a summation of this guy. And then it's a constant, and then we just take this integral from somewhere to somewhere plus t naught. So that will equals to what? So this integral equals to, right? It's like an integral of like this. A at t naught, and then we just have 1, right? So that equals to what? T naught, right? Okay, we just times t naught, and this cancels, and this is what we get. Okay, so basically it means that the power of the signal in the time domain, and then this is what we got in the frequency domain, right? We can also write that as the norm of S, right? So this bar means that it's a vector. Okay, does that make sense? So in other words, yeah, let's summarize. So basically, our power, PS, equals to this guy also equals to this guy, right? So this is in the time, and this is in the frequency. Right? Does that make sense? So this is called Parseval theorem. Okay, think about it. It is quite nice, right? As we said, normally, if I have signal that is periodic in the time domain, in the frequency domain, normally that is not periodic, right? Normally, how to say? So in the frequency domain, we can imagine this guy as an energy signal, right? Because in the frequency domain, it's not periodic. Right? Remember, if for a square wave, like this, periodic, and in the frequency, it'll be a, yeah, I forgot exactly, do you remember? So in the frequency, I think it's something like this, and then like that, this, that, this, that, something like that, right? And then the magnitude will reduce, right? So basically, you can see, although it's in the frequency domain, right? But from the definition point of view, so this guy in the frequency is like an energy signal, right? It sort of means that if we compute the power in the time, so that equal to the energy in frequency, right? But the meaning of the energy in frequency, it still means power in time. But mathematically, it's like we compute the power here. Okay, so actually it holds for any pairs, right? Yeah, as long as it exists, right? For example, for a periodic signal, we cannot compute its energy, right? Because the energy is infinity. We can only compute the power, so we compute the power, right? And for this guy, because it looks like that, we cannot compute the power. The power is 0. We can only compute the energy, right? So if you compute whatever exists, they will be equal, right? If we only have energy here and we have power here, if you compute the energy here and power here, they'll be equal. Just compute whatever exists, they'll be equal. So that's what Parseval's theorem tells you. Does that make sense? So now we see, okay, so this power equals to this energy, but the meaning of that is still power, right? So the reason we want this kind of relationship is that normally, one way is easier to compute than the other. Okay, for example, if we compute the power in the frequency domain, we don't need to do integral. We just do some summation. Okay, but here we need to do integral. Normally, that is harder. Right? Does that make sense? Okay. Yeah, so that's what I want to cover for the energy and the power in frequency. So basically, we introduce the Parseval's theorem. So yeah, we have 2 minutes left. Yeah, I don't think I will cover much for the third topic. Yeah, probably I'll cover that in the next lecture. Yeah, maybe I will emphasize one more thing here. Okay, so normally, yeah, let's maybe see one simple example. Let's say if g of t is real. Okay, if g of t is real, then what happens for g of f? So we know g of f equals to g conjugate minus f, right? If g is real, we'll have this nice property, right? So if that is the case, then yeah, let's say g is real and it's not periodic, okay, aperiodic. Then basically, if we compute the energy of g, so that will equals to, because we have this symmetry property, right? So in the frequency domain, we still compute the energy, right? We have this symmetry property, so basically we just need to compute the energy for half of it, gf squared df, and then we just multiply 2 there, right? Because the positive part and negative part are equal. You can see from this example, it means that in the time domain, it's aperiodic. In the frequency, it's aperiodic. And then we compute the energy of these two, and they'll be equal, right? If you compute the power of these two, they're all 0. It doesn't mean anything. Yes?
So does the Parseval's theorem only work with periodic signals?
No. Yeah, this is aperiodic.
But I mean the theorem above, where it's like you calculate the power in time.
Yeah. Yes, whatever exists. Right? In this case, only power exists. Energy is 0, doesn't exist. Yeah. Right? So as long as it exists, we can do that. So if only energy, if power, is infinity, it means that, if power is, if power is 0, it means that the energy exists, right? Then we'll compute the energy here, and then compute whatever exists here. They'll be equal. Yeah, you can show that. We have like many combinations, right? We have a periodic here, discrete, and aperiodic, and whatever. So there's maybe like 4 combinations. Yeah, if you compute all of them, you'll see they'll be all equal. Yeah, we're going to see other examples for sure, but now we only see that. But from this example, you can see, so if it's aperiodic, still works. Good. OK, so we're going to continue in the next lecture. Thank you.